Hello, I am Carson Weddle, and I will be presenting tumor immune dynamics with an immune checkpoint inhibitor as published in 2018 by Elpiniki Nikolapoulou et al. In Letters in Biomathematics. So for just a quick summary of the interaction that is modeled in this presentation, they are looking at the checkpoint inhibitor PD1, programmed death 1, which is expressed on activated T cells, and they're focusing on its interaction with its ligand PDL1, which is expressed on various types of tumor cells. And what the interaction that occurs is that when PDL1 binds to PD1, this allows the molecule or the cell that was expressing PDL1 to go unnoticed as a threat by the T cells. So this is used by tumor cells to avoid being attacked in the immune response. And so what they're looking at in this model is the introduction of an anti-PD1 drug treatment in hopes that it inhibits the PD1 and thus the formation of the PD1 PDL1 complex, which then will allow the T cells to attack the tumor cells uninterrupted. Now, the model that was constructed for this situation was a model of three differential equations, with the first equation modeling the growth or decay of the tumor cell population, consisting of just a net growth component and a component for the number killed by T cells. Second equation modeled the population of activated or effective T cells. So that is combined with the components of the number of T cells activated by interleukin 12, the number of T cells stimulated by interleukin 2, the number of T cells that are going to be inhibited by the formation of the PD1 PDL1 complex, and then a component that is the natural rate of the death of T cells. Then the third equation is a function that represents a drug treatment of an anti-PD1 drug. Then a component that measures the depletion of PD1 anti-PD1 drug levels through their successful blocking and the natural degradation of those drug levels over time. And that equation models the amount of anti-PD1 drug in the system. And then these three equations are just left out for simplification of the three equation models. These plug in to various parts of these three equations. All of the parameters and constants that are located throughout are obtained through other papers that we will see on the next slide. So here we have a Simulink model of the system of three differential equations. We have the differential part of the first one, the second one, and then the third one here. We have A of t, our controlled function that we can enter. And then this Simulink model is divided up by the sections that were seen on the equations. So like in the first equation, we have net growth section and then the killed by T cell section, and those combine together into the equation. And so that is consistent for the rest of the model. And then over here, we have the list of parameters that were used for the model, as well as the papers that they were obtained from. And so as you can see, a lot of these have quite large ranges, and some of them just have to be estimated because there's not enough data yet to know them for sure. And that's really the point of this model, is to create a simple model that can be used to become more accurate with these parameters so that we can get a better understanding of this inhibitor checkpoint reaction. So this model was first analyzed to determine the maximum rate of T cell death that can still allow for successful elimination of tumor cells. That value is determined to be a quarter of a cell per day. And so that just shows that a healthy immune system should be able to fight off tumorous cells, whereas a unhealthy or compromised one will not be able to. So just in these graphs, you see that dt, that rate is 0.05. So the tumor cell density decreases to 0 while the T cells maintain a healthy level. These are the graphs from the paper. This is from my simulation. And so then in that same system, that same untreated system, uh, I varied dt, that death rate of T cells, and eta, the rate at which T cells kill cancer cells, to see how the system would respond. And so in this first column, you have dt of 0.05, 0.25, 0.3. And so you can see that 0.05, you have a very quick degradation of the tumor, well, and T cells reach a healthy level. 0.25, you see that same degradation over a longer period of time. And then with 0.3, the tumor is able to grow over in the long term. Whereas in this eta column with dt being 0.3, you see that an eta at a very low value allows the tumor to grow. Same goes for a middling value with that 0.3 dt. Tumor is also able to grow, but if you get it up to a high value, such as 75 in this case, it is able to overcome that low rate of T cell death and eliminate the tumor. So just in conclusion, although this is a simple model, it is useful to be able to easily obtain clearer insights into the underlying processes of this interaction and to calculate more exact values from those parameters we saw earlier. The variation of the rate of death of T cells shows that while a healthy immune system may be able to fight off the tumor, an unhealthy one is not going to be able to. And variation of eta shows that if it were possible to increase the rate at which T cells killed cancer cells, this increased rate could make up for a high rate of T cell death and eliminate the tumor. And so here's just the reference for the paper and model used. Thank you for watching.